Okay, in this lecture, we're going to talk about operating system structures, as in data structures and operating system services. So what are operating system services? They provide an environment for execution of programs and services to programs and users. One set of operating system services provides functions that are helpful to the users, such as a UI. Almost universally there, it either is a command line, CLI, or a GUI. There can also be batch user interfaces, which tend to show up in older systems and will also show up in our semester project. Program execution. The system must be able to load a program into memory and run that program, and execution either normally or abnormally indicating an error. And then I/O operations. A running program may require I/O, which may involve a file or any other I/O device. One set of operating system services provide functions that are helpful to the user, and we're going to continue this. File system manipulation. The file system is important. Programs need to read and write files, accept directories, create and delete them, so on. Communications are also another factor, exchanging information on the same computer or between computers over the network. There are multiple approaches. There's either shared memory, or through message passing, which is packets moved by the OS from one process to another. We'll formally define what a process is later. The OS needs to be aware of possible errors that can occur in the CPU, hardware, I/O devices, and in programs themselves. For each type of error, the OS should take appropriate action to ensure correct and consistent results. Debugging facilities can enhance the user's and programming's ability to use the system. Another set of OS functions exists for ensuring the efficient operation of the system itself. Resource allocation. Multiple users or multiple jobs must allocate resources appropriately. There are multiple resources. There's CPU cycles, main memory, file storage, I/O devices, and more. Network resources. We have to do accounting. We need to keep track of what users use, how much, and what kinds of computing resources, as well as just a general auditing capability, which is becoming more and more important in the days of cloud and network computing. Protection and security. The owners of information stored in a multi-user or network computer often need to control who can see what and who can do what, and make sure that concurrent processes don't stomp on each other. Protection involves ensuring that all access to system resources is controlled. Security of the system from outsiders requires user authentications, defending I/O devices, establishing certificates and authenticity, that sort of thing. So here's a view of the operating system services. On the top level, the user level, we have our GUI, batch, and command line user interfaces. These make system calls to the various modules, and underlying all these modules are error detection and handling and protection and security. These run on top of the base operating system or kernel, and these talk to the hardware. Let's talk a little bit about a CLI, or command line interface, or an interpreter, however you want to talk about it. It allows direct command entry. You basically type, ls, and it'll list a directory. Sometimes they're implemented by computer in kernel, sometimes by system programs. Most times these days it's a system program. There can be multiple flavors implemented called shells. Linux has a ton of them. Windows, you have the traditional DOS command line. You have PowerShell, and now you have the advanced shell, as well as various Linux shells. The primary function is it fetches a command from the user and executes it. Sometimes they're built-in commands or names of other programs or batch files. The nice thing about the latter is adding new features doesn't require modifying the shell. So here's a quick example of using the Bourne shell to do various commands like pwd, print working directory, and so forth. User-friendly desktop metaphors are known as GUIs. Usually they use a mouse or keyboard and monitor, or they could use a touchpad or a pen, all sorts of fun things. They use icons to represent files, programs, etc. Mouse buttons impact objects in the interface and cause various actions. It was invented at Xerox PARC, not at Apple, and Apple kind of stole it, and then Microsoft kind of picked it up from them. Most systems now include both a CLI and a GUI. Windows is a GUI with a command line. App is a GUI with a Unix kernel underneath. And Unix and Linux have command line options with multiple interfaces, CDE, KDE, GNOME, and there's others. Now also there are touchscreen interfaces. They are in situations where you don't have a mouse or don't want a mouse, and the actions are based on various gestures, and a virtual keyboard for text entry. There's also voice commands for things like Siri, which of course, and Alexa, which do have operating systems. A quick screenshot of the Mac GUI. So let's move on to system calls. A system call is a programming interface to the services provided by the OS. It's typically written in a high-level language like C or C++ or Rust, one geared to operating system implementation. You can do it in more managed languages like C# or Java, but that's not very typical. Mostly accessed by programs via a high-level API, application programming interface, rather than direct system call use. You don't call the actual areas in the machine code, you have an API wrapping it. The three most common APIs are the Win32, actually these days Win64 API for Windows, POSIX for POSIX-based systems, including Unix, Linux, and Mac, and the Java API for the Java Virtual Machine. Now, the Java API for the JVM isn't necessarily a base part of the operating system, so to speak. It's just a wrapper around the individual operating system's APIs. For these examples, we're going to use generic calls as opposed to specific because we're just trying to get the concept across. So here's the sample call sequence to copy the concept of one file to another. We've got our source file and destination file. So the system call sequence is acquire the input file name, write a prompt to the screen which accepts input as part of that, acquire the output file name in the same way, open the input file, but if it doesn't exist, abort and throw an error, create the output file. If it exists, abort, otherwise create it. And then we loop through, read from the input file, write to the output file until the read fails, close the output file, and write the message to the screen and terminate normally. Here's an example of a standard API call in Linux. The read function in Unix and Linux. And here you can learn about it from the man page. And here's a description of the API actual call. We've got a return value, our function name, and our parameters, pretty standard. A program that uses the read functionality must include the appropriate header, unistd.h, as this defines the size and size t data types, among others, of course. The parameters are as follows. FD is a file descriptor to be read, a buffer where the data will be read into, and the number of bytes to be read, the maximum, not the actual number, which could be less. On a successful read, the number of bytes is returned. A return value of 0 indicates end of file, and a return value of -1 equals an error. Typically, a number associated with each system call at the implementation level. The system call interface maintains a table indexed according to these numbers. Basically, it's an index into the OS. The system call interface invokes the intended system call in the OS, and it returns the status. The caller needs to know nothing about how the system's call is implemented. It just needs to obey the API and understand what the OS will do as a result of the call. Most details of the OS interface are hidden from the programmer by the API, managed by runtime support libraries, etc., included with the compiler. This is good because that abstraction makes it much easier to use. The relationship between the API and a system call and the OS are as follows. The user application calls the system interface, which pops into the vector table, which takes us to the actual implementation. And then we return the value, which goes back to the system call, which pops back to the user application. So, when we pass parameters to a system call, it varies according to the OS. Three general methods are used to pass parameters. One is we could pass them in registers. But there could be more parameters than registers. Parameters can be stored in a block or table in memory, and the address of the block can be passed in a register. This is taken by Linux and Solaris. Parameters can be placed or pushed onto the stack by the program and popped off the stack by the operating system. This is commonly what's done in programming languages, not necessarily in OSs. And the block and stack methods do not limit the number or length of parameters being passed, which is kind of nice. So here's parameter passing via table. We've got our parameters for the call. We load the address of X into a register. We make our call, and it uses the parameters from the table. Here are some of the many types of system calls. We've got process control for creating, processing a process, terminating it, ending and aborting a process. We can load and execute them. We can get its attributes and set them. Wait for a time, wait for an event, or signal an event. Allocate in free memory, dump memory, and using a debugger for bugs and single-step execution, and locks for managing access to shared data. So we have to watch about sharing data between processes so we don't get into conflicts or race conditions, which we'll explain later. File management has the same create file, delete file, open and close, read write, reposition, and get and set attributes. Device management is the request the device, release device, where you avoid contention. We can read, write, and reposition, get the various attributes and set them, and attach or detach devices. We also have information maintenance. Get the time or date or set them. Get system data and set system data. And get and set process, file, or device attributes. Communications. We can create or delete a communications channel, send or receive messages. If message passing model is used remotely, you get the host name or process name from client to server. Shared memory models create and gain access to memory regions, and we can transfer status information. Attach and detect remote devices. Protection. Control access to resources. We can get and set permissions and allow and deny user access. So here's some Windows calls and their corresponding Unix ones. To create a process in Windows, you call create process. Unix is fork. Exit process is exit. Wait for single object is wait. Basically, the Linux ones are are less verbose. I've spent most of my time working in the Windows world. I prefer the long names because I think they're more explicit. Set console mode is easier to understand than IO control. Similarly, create file mapping is much easier to understand than SSM get, and so forth. System calls and library functions in Unix. Defined in the C language regardless of the actual implementation. In Unix, each system call has a function of the same name. The distinction between system calls and general library functions. General purpose functions are not entry points into the kernel. Some don't involve the OS at all. Here's a standard C library example. Printf is a library call which calls write the system call. So here's main, it calls print. It drops into the standard C library which calls write, which is a system call in kernel mode. And when it's done, it pops out to the C library, which pops back out to our application. Here's an example in MS-DOS. MS-DOS is single tasking. The shell invoked was when the system is booted. Has a simple method to run programs. It doesn't share processes, so no process is created. It has a single memory space. Loads programs into memory, overwriting all but the kernel. Program exit means the shell is reloaded. It's very simple, no contention, but also limited in its abilities. FreeBSD, a Unix variant, has multitasking. The user login invokes the user's choice of shell. The shell executes fork to create a process and exec to load programs. The shell waits for the process to terminate or continues with user commands depending on how they're done. And the process exits with either no error or an error code. Here we've got our process, free memory, another process. We've got our interpreter process, and it calls all these others. Okay, then there are the concept of system programs. System programs provide a convenient environment for program development and execution. They can be divided into various categories: file manipulation, status info, programming language support, programs loading and execution, communications, background services, and application programs. Most users' view of the operating system is defined by the system programs, not the actual system call. ls, for example, to list a directory, we don't look at the get directories beneath it. They provide a convenient environment for program development. Some of them are simply user interfaces to system calls. Others are considerably more complex. So for file management, we have our standard create, delete, copy, etc. For status information, some ask the system for info. Others provide detailed performance and logging info. Typically, these programs format and print the output to the terminal or other devices. Some systems implement a registry, Windows does, used to store and retrieve configuration information. For file modification, we often have programs like system text editors, although most of the built-in ones kind of suck, and special commands to search contents of files, etc. Programming language support, compilers, assemblers, debuggers, and so forth. Programming loading and execution, absolute loaders, relocatable loaders, linkage editors, overlay loaders, and so forth. Communications provide the mechanism for creating virtual connections among processes, users, and computer systems. It allows users to send messages to another screens, browse web pages, etc. Then there are background services, which typically launch at boot time. Some for system startup and then they terminate. Some for system boot and to shut down. They provide facilities like disk checking, process scheduling, etc. They run in the user context, not in kernel context, and are typically known as services, subsystems, or daemons. Application programs don't usually pertain to the system. They're run by users and not typically considered a part of the OS. They're launched by various mechanisms, command line, point and click, etc. The design and implementation of an OS is not solvable as a problem, but some approaches have proven successful. The internal structures of different operating systems can vary widely. You start the design by defining your goals and specifications, affected by choice of hardware type of system, needs. User goals and system goals also weigh in. User goals, the operation should be convenient to use, easy to learn, reliable, safe, and fast. The system goals could include the operation should be easy to design, implement, and maintain, as well as flexible, reliable, error-free, and efficient, and ideally extensible. An important principle to separate is a policy, what will be done, from a mechanism, how to do it. There's also the question of why. Mechanisms determine how to do something. Policies decide what will be done. The separation of policy from mechanism is a very important principle. It allows maximum flexibility in policy decisions are to be changed later. For example, timers. Specifying and designing an OS is a highly creative task of software engineering. It's also one of the hardest, honestly. There is much variation. Early OSs were originally written in assembly language. Then there were languages like Algo, PL1, C, C++, and languages now like Rust. There are even some OSs like Coherence implemented in managed code like C# or Java. Nowadays, operating system development uses a mix of languages. Lowest levels are typically done in assembly, the main body in C, C++, or Rust. System programs in C, C++, Rust, Perl, Python, anything else. And high-level languages are also used. High-level languages are easier to port, and although this is but slower, that is often not the case anymore because optimizing compilers can often compile code to assembly which is more efficient than ones that programmers can do. Emulation can allow an OS to run on non-native hardware. A general-purpose OS is a very large program, and there are various ways to structure them. Very simple structure is MS-DOS. More complex is Unix. Then we can have layered, which is a set of abstractions, or a microkernel, which an example of that would be the Mac operating system. So let's look at MS-DOS. It's written to provide the most functionality in the least space. It's not divided into modules. It has some structure, and its interfaces and levels of function are not well separated. It was a very early operating system. So a more complex structure is Unix. It's limited by hardware functionality. The original Unix had limited structuring. The Unix OS consists of two separate parts, the system programs and the kernel. It consists of everything below the system call interface and above the physical hardware. So basically it presents a virtualized view of the machine. It provides the file system, CPU scheduling, memory management, and other OS functions. And it's a lot of functions for one level. Here's a traditional view. It's not layered, though. Not fully layered. We've got shells and command interpreters, etc., system calls to the kernel, and then the kernel interfaces with the hardware. Then there's the layered approach. The operating system is divided into a number of layers, each built on top of lower layers. The bottom layer is the hardware. The highest layer is the user interface. So here we've got layer 0, hardware, layer 1, etc. With modularity, layers are selected such that each uses functions and services of only lower level layers. So layer 0 would never call something in layer 2. A microkernel system structure moves as much from the kernel into user space as possible, very light. Mach is a good example. The Mac OS kernel is partly based on Mach. Communication takes place between user modules using message passing. Okay. The benefits are it's easier to extend, easier to port because you've only got a small piece to port. It's more reliable and more secure. However, there can be some performance overhead of user space to kernel space communications. So here's a microkernel structure. We've got the application program, the file system, device driver, etc. Here we've got some basics. Inter-process communication, memory management, and CPU scheduling. That's all that's in the microkernel, and the microkernel is the only thing that talks to the hardware. Many modern OSs implement loadable kernel modules. That's more of an object-oriented approach. Each core component is separate, and each talk to the others over known interfaces, and loadable as needed. It's similar to layers, but it's more flexible. Here's an example of Solaris. Devices and bus drivers, scheduling and classes, etc. all talk to the Solaris kernel. And you can add more, and they'll still talk to the kernel. There are hybrid operating systems. Most OSs are not a pure model. Combines multiple approaches to add performance, security, etc. Linux and Solaris kernels in kernel address space, so they can be monolithic, plus modular for dynamic loading of various functionality. Windows is mostly monolithic, plus microkernel for different subsystem personalities or views. Apple and the Mac OS is hybrid. It has a UI plus Cocoa programming environment, which has been supplanted these days by the more modern Swift environment. So here's another example. In a Mac, we've got our user interface, the environment and services, the various languages, and the kernel environment. We've got Mac and features of BSD, and the I/O kit for connecting our devices and the kernel extensions. iOS is a mobile operating system. It's roughly based on Mac OS. It doesn't run OS X applications natively, only iOS applications. It can run on different CPU architectures, although these days it's limited more and more to Apple's M2 stuff. Cocoa Touch is an Objective-C API, or these days a Swift API for developing apps. There's media services, core services for cloud computing, etc., and a core operating system based on Mach. Android is another one, and it's developed by the Open Handset Alliance, which is mostly Google. It's open source. It has a somewhat similar stack to iOS, and it's based on Linux, but modified. It adds power management to the basic kernel. Runtime environment includes core sets of libraries and the Dalvik virtual machine. And apps are typically developed in Java plus an Android API, although these days you can develop in C#, all sorts of other languages. Java class files are compiled into Java bitcode, then translated. One of the nice things about Java bitcode is you can generate it from other languages as well. Libraries include frameworks for web browsing, database, etc. Here's the same architecture. We've got our application framework, our various libraries, and then here we have our core library is essentially the core and our VM. How do we debug an operating system? Debugging is finding and fixing errors. The OS typically generates log files. A failure of an application can generate a core dump, capturing the memory of the process. Operating system failures can generate crash dump files containing kernel memory too. Beyond crashes, performance tuning can optimize system performance. You can use trace listing of activities, profiling. Kernighan's law. Debugging is twice as hard as writing the code in the first place. Therefore, if you write the code as cleverly as possible, you are by definition not smart enough to debug it, because it's twice as hard. Don't be clever, be consistent, write good code that works well and cleanly. OS is typically performance tuning by removing bottlenecks. It has a means of computing and displaying these metrics. And in Windows, for example, you use the Windows Task Manager. In Unix, you often use dtrace to do this sort of thing. And here's some just overviews of dtrace, which you can look at. Operating systems are designed to run on any of a class of machines, but you must configure them to individual systems. Sysgen is a program that obtains information and builds system-specific kernel compilations for those. And it can often generate more efficient code. That's a Linux thing, by the way. When power is initialized on system, the execution starts at a fixed memory location. Firmware ROM, or flash RAM, is used to hold the initial boot code. The operating system must be made available to hardware so the hardware can start it. A small piece of code, the bootstrap loader, is stored in ROM or EPROM. The kernel loads it into memory and starts it. Sometimes it's a two-step process where the boot block is at a fixed location and it's loaded by ROM code, which loads the bootstrap loader from the disk. A common bootstrap loader for the Linux world is Grub, and it allows selection of the kernel from multiple disks, versions, or kernel options. You can run multiple operating systems. The kernel loads and the system is then running. So this is just a high-level overview of all the various structures in an operating system.